Let's get started with lecture 18. So today we're finishing up our discussion of the Doppler effect. So we'll talk about the Doppler effect also for light. And then I want to spend most of this lecture on problem solving. So reviewing what we did in chapter 16 and solving various problems. All right, so last time we introduced the Doppler effect for sound. So we talked about Doppler effect for sound, and we discussed two different scenarios. So one is you have a source that's moving at speed, let's say Vs, the source, and you have an observer. And the source emits sound with frequency f naught, so that's the natural frequency of the source. So the idea is that the frequency that this observer here perceives or receives is larger, because basically these wavefronts, as the source is moving, have to get squished together. The distance between consecutive wavefronts, which is the wavelength, gets smaller compared to the case where the source was stationary. So here this observer measures a frequency f plus, that's f naught divided by 1 minus Vs over V. And another observer over here, where the source is moving away from him, will measure a frequency that's smaller or lower. So that's going to be f naught divided by 1 plus Vs over V, where V is speed of sound, or speed of the propagation of these waves in the medium. So as long as all these speeds are much smaller than the speed of light, these expressions hold. We also considered another case where the source is stationary, source, and then the observer moves, for example, in this case, toward the source with speed VO, or V observer. Okay? So in this case, again, when they're moving toward each other, again, more wavefronts hit the observer in unit time because it's moving into those wavefronts. And the frequency goes up. So here there's f plus, which in this case is given by f naught 1 plus V observer over V. And of course, if the observer is moving this way, she perceives a lower frequency given by f naught 1 minus V observer over V. Okay, so let's have a quick practice problem with this. Yeah, we talked about those. Okay, so here's the problem. Okay, so yeah, so let's read it together. So the police siren has a frequency of 550 hertz as the police car approaches you, 450 hertz after it has passed. So when it's approaching you, you would hear a higher pitched sound, higher frequency. And when it passes and is receding, there's this smaller frequency. So the question is, how fast are the police traveling? And the problem gives you the temperature, so there's something you should look up, so I've written it here. The speed of sound in air at those temperatures, like 20 degrees centigrade, is, you can assume it's 343 meters per second. So the temperature is basically just determining the speed of sound. All right, so pause the video, try to work this out, and then we come back and look at it together. Okay, so let's go to the notes and try to figure this out, right? So here we have moving source, right? The siren is moving and the observer or the listener is stationary. So this is example 1611. Let's see, example 1611. So here we have the observer. First, the police car is moving this way, the source, and there's an F plus that the observer hears, which is 550 hertz, I believe. 550. And then when the source is moving away, there's an F minus that you hear, that's 450 hertz. Okay, and the speed of sound v is 343 meters per second. So v is 343. Okay, so let's go back to our formulas, right? So for the case of stationary observer, moving source, so we know that F plus is F naught over 1 minus Vs over V, right? So F plus is F naught, the frequency of the siren, 1 minus Vs over V, and F minus, this frequency is F naught 1 plus Vs over V. All right, so we're interested in finding Vs, how fast the police car is moving, what is the velocity of the source, what is the speed of the source. And in this equation, in this system of two equations, we have two unknowns, right? So we don't know F naught, we don't know the natural frequency of the siren. We also don't know Vs. We know V, we know the speed of sound, and we know those frequencies that the observer measures. So F plus and F minus are known. So the fastest way to solve this is to get rid of F naught, and we can do that by just dividing these two equations. So we can write F plus over F minus, then the F naughts cancel out, is going to be 1 plus Vs over V, 1 minus Vs over V. Okay? So this gives me what? I want to solve for Vs from here, right? So let's multiply by 1 minus Vs over V and multiply by F minus. So then I get F plus times 1 minus Vs over V is F minus times 1 plus Vs over V. F minus multiplied by 1 plus Vs over V. So this gives me F plus minus F plus Vs over V is F minus plus F minus Vs over V. So I bring the terms that have Vs together. So that gives me, let's take this term to the other side. I find F plus F minus times Vs over V is, I now take this F minus to this side, it gives me a minus sign, so that's F plus minus F minus. So from here we find that Vs over V is F plus minus F minus over F plus F minus, and therefore Vs is V times that whole thing. F plus F minus. Okay, So I believe the numbers were 450 and 550, so their difference is 100, right? Their sum is 1,000. So that's going to be just the speed of sound, which is 343, so we're going to get 34.3 meters per second. All right, so basically making use of the equations to solve for Vs, the speed of the police car. If the problem had asked also for the frequency, for the natural frequency of the siren, now that we have Vs, we can go into either of these equations and solve for F0, right? Now that we know Vs, we can write F0 to be F minus, which we know times 1 plus Vs over V, and we can solve for it. All right. Yep, so that's basically the answer. Now, here are the expressions for light. So again, qualitatively, it's the same kind of phenomenon. So if you have a source of light that's moving toward you, is approaching you, that implies that you measure a higher frequency and a smaller wavelength. So here in this expression, the second one, lambda plus, corresponding to higher frequency, for an approaching source, you see the coefficient of lambda naught. Lambda naught would be just a natural wavelength that the source emits. So it's basically the speed of light divided by the natural frequency of the source. It gets multiplied by this factor. 1 minus Vs, the speed of the source, over C, the speed of light, over 1 plus Vs, over C, the whole thing under square root. So that's a consequence of the special theory of relativity. We won't be able to derive this here without doing a lot of background work. So these are two expressions that we take and use in this course without proof. And for a receding source, basically the only thing that changes is that the sign of Vs changes, and that gives you a larger wavelength and a lower frequency. All right, so let me write these two expressions in the notes. So we have them. Yeah, so these are the two equations that we need to study the Doppler effect for light, and it's easy to convert this to an equation for frequency, because we know that, let's say, lambda plus, for example, is the speed of light divided by the frequency that this observer measures, and lambda naught is similarly C over the speed of light over F naught, the natural frequency of the source. So putting these expressions into the equations for wavelength, we find, and similarly, let's say lambda minus is C over F minus. So from these we find that F minus becomes, so 1 over F minus is that coefficient times 1 over F naught. Therefore, F minus is the inverse of this coefficient times F naught, right? So it's going to be 1 minus Vs over C, 1 plus Vs over C, F naught. So as you see, the frequency in this case goes down, and F plus, similarly, you have the inverse of this, which is 1 plus Vs over C, 1 minus Vs over C, F naught. All right, let's also look at one example on the Doppler effect for light. So that's our example. So it says it's basically a practical way of measuring the velocity of a galaxy, of a faraway galaxy. So the idea is that hydrogen atoms in a lab emit red light with wavelength 656 nanometers. That just has to do with the energy levels of a hydrogen atom, and they emit light because you have electrons transitioning between these levels. So it has to do with the difference between the energy levels of that atom. It's a characteristic wavelength in the spectrum of hydrogen. And then this is called a spectral line. Now, if you observe the light from a faraway galaxy, this particular spectral line is observed at a larger wavelength, right? So the question is, what is the speed of this galaxy relative to the Earth? And also try to think about whether it's moving away or moving toward the Earth. So yeah, so let's try to pause the video and solve this problem. Okay, so we observe a larger wavelength, right? A lower frequency. That means it must be moving away from us. And that's called being redshifted, because lower frequencies, longer wavelength are on the red side of the visible spectrum, and blue and violet have higher frequency, lower wavelength. Now, okay, so let's just solve for it. We just want to use our equation and solve for Vs, right? It's for a source that's moving away. Let's see, it was example 1612. All right, so example 1612. So we have a source that's moving away. We're measuring a larger wavelength. It's a receding source, so that's the relevant equation, right? Lambda minus is square root of 1 minus Vs over C over 1 plus Vs over C. That's this coefficient over here. No, that's not the correct answer. Lambda must get larger, right? So that's plus, that's minus times lambda naught. Okay, so we know this, we know the natural wavelength emitted by hydrogen atoms. We know the wavelength that we measure. So let's see what they were. So lambda naught, according to this problem, is 656 and lambda, and the other one is 691. Okay, so that's 656 and lambda minus is 691. Okay, so we know those. We know the speed of light, which is 3 times 10 to the 8th meters per second. So, okay, so we're good, right? So we just need to solve for Vs, right? So let's see how we can do that. Well, we can write lambda minus over lambda naught is that square root 1 plus Vs over C 1 over 1 minus Vs over C. We can square both sides to get rid of the square root. So therefore, lambda minus over lambda naught squared minus lambda minus over lambda naught squared times Vs over C is equal to 1 plus Vs over C. So we collect the terms that have Vs over C in them on one side. So bring this one to this side. So we find lambda minus over lambda naught quantity squared minus 1. We take this term to the other side, factor out Vs over C, so we get 1 plus this quantity. And finally, we divide by this coefficient, we multiply by C, so we find Vs is given by C times lambda minus over lambda naught squared minus 1 over lambda minus over lambda naught squared plus 1. Okay? So we just then plug in the numbers, right? Lambda minus is 691, this is 656. We plug them in, and let's see what the answer is here. Yeah, so that's the expression. We just put in the number, so it's going to be 1.56 times 10 to the 7. Notice that because the ratio of lambda minus and lambda naught appears, you don't need to convert these to meters as long as they have the same dimensions, right? So as you divide them, you get a dimensionless number. So we must make sure that those two wavelengths have the same dimension. All right, so we discussed two versions of the Doppler effect. One applicable to sound, and the other can be used for light. All right, let's solve a few examples from the end of chapter. So this is a problem 1663. So it says there's a sinusoidal wave that travels along a stretched string, and a particle on the string has a maximum speed Vmax and a maximum acceleration Amax. So the question is, find the frequency and the amplitude of the wave. So pause the video, try to spend some time and figure out the solution. All right, so what can we say here? So again, traveling sinusoidal wave in one dimension, so that's the general expression for the displacement at distance x times t. There's going to be the amplitude times sine kx, the wave number, minus omega t, plus phi naught, the phase constant. And then it's talking about the speed and acceleration of a particle on the string. So it's a physical motion of a piece of this string in the perpendicular direction to the direction of the propagation of the wave. So those, remember, come from taking the derivative of this expression with respect to time, fixing x constant, right? So if you have this traveling wave, you look at one cross-section, at that point you have simple harmonic motion up and down, and you fix the x, so the time dependence is just given here, and then we can take the derivative, so that gives me minus omega a. The derivative of sine is cosine of the same phase. And the acceleration, I take another derivative, so there's another factor of minus omega, that gives me omega squared. The derivative of cosine is minus sine, so that becomes minus omega squared a sine. And time keeps moving, so these sines and cosines as a function of time, regardless of what x is and what phi naught is, will fluctuate within a range of -1 to 1, right? So therefore the maximum speed will be a omega, and the maximum acceleration we can read off from here is a omega squared. Okay, so then we're in business, right? So we have two equations and two unknowns. So the unknowns are a and omega. We can solve for them. And the frequency is just related to omega by a factor of 2 pi, right? So omega is 2 pi f. F is omega over 2 pi. So if we just calculate omega, we're done. We know f is just divided by 2 pi, and that's it. Okay, so it seems an easy way to proceed is to divide these equations to say a max divided by v max is just omega. So we're done with that. So f is a max over 2 pi v max. And then to find a, the amplitude, let's plug it in. So plug it into, for example, the first equation. So we have v max is a omega, which is a times a max over v max. So from here we can solve for a. A becomes v max squared divided by a max. All right. So when we talk about maximum acceleration and maximum speed, the only observation is that these sines and cosines go between -1 and 1 and realize all the values in between them. So here's another problem. It's slightly more tricky. So let's read it together. So the question is the displacement d of x and t given by that function, 0.1 minus 0.1 times x squared plus xt minus 2.5 t squared in meters, where x is in meters and t is in seconds, is it a possible traveling wave? In that case, what is the speed of this wave? So think for a few minutes. I'll give you a hint. Remember, generally for a pulse or a wave that's moving with constant speed, d of x and t must have the property that it's a function of x minus vt if it's moving to the right, or x plus vt if it's moving to the left. So we need to figure out if this particular function has that property. All right, so I hope you managed to find a solution here. So yeah, so that's what's given to us. So for example, let's see how it looks like at t equals 0. So let's say this is x, right? At t equals 0, so those two terms go away. And when x is 1 and minus 1, I think it's 0. And then here, so let's say that's d. At x equals 0, it's 0.1. So it's somehow an inverted quadratic form. It's a displacement like that extends, to infinity. And then a little bit later, want to see what it looks like. So how about I put, that's right, so let's say that's the shape at t equal 0. So the question is, at later times, does it look like the same thing except shifted to some other position? So will it look like something like this? If that's the case, it's a traveling wave, right? It doesn't change its shape, it just gets translated along the x-axis. So it seems if it's a function of x minus vt, for example, then the only thing it can be is a quadratic form, right? Because it's a polynomial, and the highest power of x in it is x squared, and also p squared. So can we make some progress that way? So let me try to take this form and manipulate it a little bit. So let me write d of x and t as 0.1, and kind of factor out that 0.1 here. So I get x squared minus 10 xt plus 25, right? 25 times 0.1 is 2.5. 10 times 0.1 is 1. T squared. And this we already can now immediately notice that this is an expansion of x minus 5t squared, right? Remember, a minus b squared is going to be a squared minus 2ab plus b squared. So that's just an identity. So here we see that it works as that. It has that form. So yeah, so it is a function of x minus something times t, and that something is 5 meters per second. So v is 5 meters per second, and that's it, and it's moving to the right with that speed. So for example, if t is equal to 1 second, right, you would just go here, right? For x equal 5, this term becomes 0, and you just get the 0.1, and then it just decays in a similar way. So let's say t equal 1, here x equal 5 meters. All right. So yeah, so waves and pulses, you know, can have general forms, even though we focused on sinusoidal waves primarily, but we can have pulses with arbitrary shapes. This problem is a little bit strange because this displacement, or whatever it is, kind of diverges at large x's, but so if x goes to infinity, for example, it goes to infinity at any time. But yeah, so it's a little bit unrealistic, but from a pedagogical point of view, it's an interesting problem that we can detect this pattern of x minus vt appearing and then just read off the speed of the propagation. All right, so finally let's look at a more challenging problem. So it's problem 1682, and at the end of the chapter, you know, toward the end, there are several problems in a section called challenge problems. So these are problems that typically need like more time, and you need to think a bit more. So yeah, typically they're harder than what appears on homework and exams. But I really like this problem, so let's think about it. So what does it say? It says there's a rope of mass m and length L, and it hangs from the ceiling. So that's the ceiling. You have a rope, and it has length L and total mass m, right? And it's hanging from the ceiling under its own weight. So part A is saying show that the speed of the wave, a distance y from the lower end, so somewhere here, somewhere here, where this distance is y from the lower end, the speed that a wave or a pulse travels at that point is the square root of g times y. So it's an interesting case where the speed of propagation is a function of where you are along the rope. Well, how do we find this? Well, it's rather simple, right? We know the general expression for the speed of propagation. It's the square root of t, the tension, right, over the linear mass density. So the linear mass density for this rope is fixed. So we know v is the square root of t tension over mu, and mu is just m over L. But what is the tension? Well, the tension changes, right, as a function of where you are. Therefore, you get this different speed as a function of where you are. So if I look at this cross section, so let's say that's my rope. Say here I have a length L minus y, here I have the length y. So if you think about this lower piece and think about the free body diagram, well, there's a tension at the point I'm interested in, right? What's implicit is the tension where you find that speed. So at that point, the distance y, let's call that the tension. And then there's the weight of this piece, which is its mass, and its mass is y times mu, right? Mu is the linear mass density, how much mass you have per unit length, which is the total mass divided by L, and you have to multiply that by the length of this piece to find the mass of this piece, and of course times g, so that's the force of gravity on this piece. And if the rope is just hanging, well, T is y mu g, so that's it, right? So we just plug it in. So V becomes y mu g divided by mu, and that's square root of gy. Okay, so that was the easy part of the problem. We just draw a free body diagram and we find the speed of propagation at a particular point along the string. Now part B is quite interesting. So how long does it take for a pulse to travel the length of the string? So if I, for example, take the bottom, move it quickly this way and bring it back, so I generate a pulse at the end, then this pulse will propagate away, so it's moving up along the string. Well, you see, at that point it's moving very slowly. It actually has a speed 0, right, if y is 0. But as soon as it moves a little bit away, its speed increases. So the farther it goes, this pulse from the source, it moves faster, right? Because the tension is increasing. So how can we relate this to the time? Well, what does it mean when we say the speed at that point is v? So it means if I look at my rope here, let's say at this distance y, well, if you look at a tiny piece of length dy, and it takes a time dt over here for the pulse to move from here to here, it means dy over dt, right? That ratio is v, which is square root of g times y. Okay, so now we want to find the total time. How should I do it? Well, I should add these tiny dt's, right? So there's a tiny dt to travel a tiny distance dy when you're at a height y from the bottom of your rope. So from here I can write dt, right, divided by 1 is dy divided by square root gy. Now, if I'm adding all those times, each of those little times is this infinitesimal dy times a function of y, and y runs from 0 to L, right? That's the full length of the rope. So total time is the integral, let's say, from 0 to t, the total time of dt, which is just t, and that's the integral from 0 to L of dy over square root g times y, let's say, to the power minus a half, right? That's 1 over square root y is y to the minus a half. Okay, so what is the integral of y to the minus a half? It's y to a half times 2, right? Because the derivative of this is just y to the minus a half. So this integral is going to be square root g, a factor of 2 that I pull out, and then we have square root y calculated from 0 to L, so it gives me 2 square root L over square root g. And that's our answer. So we're saying time, or total time for travel, is 2 square root of L over g. Okay, so we're done with chapter 16, so let's review briefly some of the things we talked about in this chapter. And then next time we start talking about superposition. So thinking about scenarios where you have more than one source putting oscillations or putting pulses into a system that propagate. All right. So yeah, so here we talked generally about the wave model in this chapter. We talked about 2 types of waves, transverse and longitudinal. We talked about mechanical waves, electromagnetic waves a little bit. We just mentioned that the quantity that fluctuates is the electric field and the magnetic field, of course. We talked about these dual pictures of describing traveling waves, the snapshot figure, the snapshot graph, the history graph. In one, time is fixed, in the other, distance is fixed. A very important equation describing general sinusoidal waves. We talked about that. We had the amplitude, we had the wave number, angular frequency, phase constant. We had this very useful picture that allowed us to visualize waves in higher dimensions, in 2 and 3 dimensions, based on wave fronts that are separated by wavelength lambda and expand at the speed of wave propagation with speed v. We had the speed of transverse waves along a string. There was another equation that we didn't really discuss, so we're not going to use this. So for sound waves, basically there's a number. Yeah, so we didn't discuss how things depend on density, etc. But yeah, there's that typical air temperature. We know what the speed of sound is, and we also know the speed of light traveling in vacuum. And we define the index of refraction. So if you go into a material, the speed of propagation of light becomes c over n. We introduced intensity, which is power divided by surface area. We introduced decibel as a unit for sound intensity level. We had some practice with that. We talked about the Doppler effect for both the case where the source is moving and the case where the observer is moving. So the frequencies change. We had the Doppler effect also for light. That's not written here, but it had a different expression. All right, that's a good place to stop.